Here we're in chapter 4, and we're going to look at the exercises 9 and 11a. So these were the ones right after spring break. Notice I'm not doing a self-test right now because they do have better explanations in the book there. So at number 9, of course we don't have any answer at all in the solution manual, so it's a good one to go over here. And what this one is, it's telling us to repeat example 1c, which we have these 20 balls in an urn. We're pulling out 4 of them, but the difference now is that after we pull one out, we're going to put it back in. So we're going to replace the balls after we draw them. And the question is, well, there's 2 questions. One, if we're going to sample 4 balls from the urn and let X represent the highest number on any of those balls that we get, what do we what's the probability of getting a specific X value? That's the first question. Then the second question, which is actually easier, is what's the probability that our X, so the highest ball out of the 4 that we draw, will be greater than 10? So two related questions there. Because they don't have any solution here, I made some ugly chicken scratch. But we can see that here the probability of getting X less than or equal to I. Now what is I? We can choose I to be anything. So X is the highest ball. So let's say we wanted I to be 5, for example. This would look at the probability that the highest ball is either 1, 2, 3, 4, or 5. So we would take all the values up through 5. So the probability that the highest out of those 4 is going to be 5 or less. And notice that we can get that really quickly from independent. We're assuming they're independent draws here, because each time we draw it, we have I different balls that would be less than or equal to I. What do I mean by that? So if I is 5, for example, there's 5 balls that would be less than or equal to 5. 1, 2, 3, 4, and 5. So in that first draw, we would have a 5 in 20 chance, or an I in 20 chance of getting something less than or equal to whatever our I is. And then the second, we would also have I in 20. Third, we have I, because they're independent, we have I over 20 every time. And since we're doing 4 draws, we would just take I 20 to the 4th. Notice that this is the same as capital F of I. So what's that? This is our CDF here. So CDF tells us everything up to or equal to this I, the random variable values up to or equal to this value of I. What's the probability of that happening? So we can just say capital F of I. So this and this are equivalent things that we're looking for, and this then gives us what we're looking for. Notice I probably should have wrote this in here somewhere, but I does have to be between 1 and 20, so maybe I'll put that in there. 1 is less than or equal to I, less than or equal to 20, because it wouldn't make sense if I was 21, then we'd have 21 20ths, so we'd have a probability that was higher than 1. Okay, but that's not what we're looking for. We're looking for what's the probability of getting exactly a specific number as our highest. So although this would tell me that all the balls are less than or equal to 5, it wouldn't tell me the probability that my highest ball is 5. Because I could, for example, get 1, 2, 1, 4, in which case I would satisfy this probability, but my highest ball wouldn't be 5. So how do I do that? Well, there's a cool little trick, and this is an important one because this is going to come up in exponential distributions when we get into continuous distributions. It's also part of the geometric when we're looking at discrete. So this is a very important little trick. So we take probability x equals 1 would be the probability of getting less than or equal to 1, which is what we just saw here, minus this portion that we don't want, the probability of getting up to or equal to I minus 1. So essentially this gives us all the way from negative infinity up to exactly the point we want. But the problem is we have all this excess waste, and then this trims off that excess waste. This takes away the probability of getting a 4 as the highest ball, or a 3, or a 2, or a 1 as the highest ball. So that we're left, once we take this difference, we're left with only the probability of getting our 5, or whatever we choose I to be, as our highest ball. And then the probability that x would be greater than 10, well, it's probably easiest to flip this around. 1 minus the probability that we're less than or equal to 10, which, again, another way to write that is just the CDF f of 10. So this is all the probability of getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as our highest ball out of the 4 draws. And if we subtract all those, we're left with only the times when x is greater than 10. Okay, let's go back to the answer sheet here for 11a. In 11a, we're looking at an integer n selected between 1 and 1,000. Each integer has the same chance of being selected. What's the probability that this random number we choose between 1 and 1,000 will be divisible by 3? Well, you might think it would be 1/3, but if you think a little more carefully, if you think of all the numbers between 1 and 1,000, which ones are divisible by 3? Well, 3, 6, 9, basically 1 through 333 times 3. So 3 times 1, 3 times 2, 3 times 3, all the way up to 3 times 333. So there's 333 of them. Over 1,000, which is slightly less than 1/3. So why is that? Well, we're cycling through these 3 numbers, 1, 2, and 3, divisible by 1, 2, 3, 1, 2, 3. When we divide by 3, a remainder of 1, 2, 3, 1, 2, 3. But then we throw in this extra one that has a remainder of 1, the number 1,000. So if we just looked at random numbers between 1 and 999, then we would get exactly our 1/3. But because we have that kind of leftover right at the end, it's not quite 1/3. Same thing for these others, the 7, the 15, and the 105. In all of those cases, because none of those divide evenly into 1,000, we're not going to quite get the exact probability that we would expect to. And let's see, yeah, this number's correct, this one's not. Okay, however, if instead of choosing 1,000, between 1 and 1,000, we were looking at between 1 and 10,000, then 1 and 100,000, 1 in a million, and in fact we're just going to let that power of 10 go to infinity, of the number of balls that we're selecting from, well, as we get closer and closer to infinity, that leftover portion that we might get becomes less and less significant, and so we're converging to a limit of what we would expect: 1/3, 1/7, 1/15, and this should be 1/105th. So this is a typo, should be 1 divided by 105. The second question gets a little more intense, but it is kind of cool because it's related to the Riemann hypothesis, so you may want to check that out, but it's a bit beyond the scope of our course.